Hello. In the last lesson, we discussed Rutherford model of the atom, and we found that there are some problems with it. Well, this is the way models in science actually develop. When we try to explain something, it should account for observed phenomenon. Well, we have a lot of observed phenomenon that can be used to explain the models of the atom. Now, what are some of the common phenomena that we should be looking at when we talk about atoms? Well, let me show you one simple example. A scientist named Bohr, I'm sure most of you must have heard about Niels Bohr. Now, Niels Bohr was familiar with the emission spectrum of hydrogen. Now, what is the emission spectrum of hydrogen? Here I have in my hand a hydrogen source. In fact, the light you see is actually emitted by hydrogen. Now, what happens to it when this light is passed through a prism or something that can actually split this light? Let me see if I can show that to you. Well, this is the normal hydrogen source, and I'm going to pass the light emitted by hydrogen through what is called a grating and see what you get on the screen. Watch that carefully. Now, you get what kind of colors? Look at the colors carefully. You get blue, green, yellow, red, and all these kind of colors. Now, any model of the atom that we propose or anybody else propose must explain this observed phenomenon. How is it possible that light emitted by hydrogen is made up of these colors? Well, that is what Bohr attempted to do. Let's look at what Bohr said. Bohr observed that when light produced by a hydrogen source is passed through a prism, it splits into discrete colors, that you can pick one color from the other. In my demonstration, I used a grating. Well, in the case of the prism, it will look like this. Now, each color in the spectrum corresponds to a particular energy of radiation. This is where Bohr actually nailed the atom model. He said each color must correspond to a particular energy. That means the structure of the atom must explain that particular energy for each color. Now, this is actually what you saw in the demonstration. Now, since these radiations come from atoms of hydrogen, Bohr argued that an atom can only emit radiations of a certain frequency. That means an atom cannot radiate all kinds of frequencies at the same time. It can only emit discrete frequencies. Certain frequency, and then the next one is certain other values. There is nothing in between. So whatever model of the atom we subscribe, it must be able to explain these discrete energy values of the radiations. Well, so what did Bohr do? So Bohr connected this idea to the model of the atom that he proposed, and he came up with 4 postulates. These are important postulates, and let's take a look at each of these postulates. Postulate number 1, he said electrons assume only certain orbits around the nucleus. It cannot assume any orbit. It can only assume certain orbits around the nucleus, and these orbits are stable and are called allowed orbits. Now, what is the problem we discussed in connection with Rutherford model? According to Rutherford model, an electron moving around the nucleus must to radiate energy, and therefore it must lose energy and ultimately fall into the nucleus. Now Bohr said, well, although there's a theory which says that at these allowed orbits no radiation do take place. In other words, these orbits are stable. You see, there are very many physical theories which defy explanations. In fact, the boldness of scientists to come forward with such postulates which can be experimentally tested is the core of many of these scientific principles. This is one such thing. Bohr said there are certain allowed orbits around the nucleus where electrons will not radiate energy, and therefore those orbits are stable. In other words, here is an allowed orbit, another allowed orbit, an orbit in between is not allowed. There cannot be any orbit in between. So only certain orbits are allowed. Each orbit has an energy associated with it. For example, the orbit closest to the nucleus has an energy E1, and the energy of the next orbit is E2, and so on. In other words, we can assign each orbit an energy value, and that is the core of Bohr's model of the atom. The third postulate that Bohr came forward with is light is emitted when an electron jumps from a higher orbit to a lower orbit, and absorbed when it jumps from a lower orbit to a higher orbit. Now, where is the energy of the electron more? Is it in the inner orbit or in the outer orbit? You know, in mechanics we talked about the potential energy. The potential energy is greater as the distance between the objects increases. Is that right? And therefore, the energy of the inner orbit, E1, is less than the energy of association with the second orbit, is less than the energy associated with the third orbit, and so on. So light is emitted when an electron jumps from a higher orbit. If an electron from orbit 2 jumps to orbit 1, now in order to be in orbit 2, an electron has to have a certain amount of energy. And if that electron is going to stay in orbit 1, its energy has to be less. So if an electron jumps from this orbit to here, it has to throw away the extra energy. And this thrown away energy is what you see as light. Light is emitted when an electron jumps from a higher orbit to a lower orbit, and is absorbed when it jumps from a lower to a higher. If an electron has to move from the first orbit to the second, it has to absorb some energy from some external source. And when an electron moves from the second orbit to the first, it throws away that extra energy. And you can see how this principle is so well suited to explain Bohr model of the atom. And the fourth postulate, the energy and frequency of light emitted or absorbed is given by the difference between the two orbit energies. In other words, when there is an electron transition taking place from one orbit to the other, the extra energy is radiated, and the frequency of radiation, each radiation has a certain frequency, and that frequency depends on that energy difference. Well, we will talk about that as we move on. Now, Bohr argued that the angular momentum of the electron in an orbit is quantized. What's the meaning of that? The angular momentum is quantized. It means that the angular momentum of the electron can only have certain values. That's the meaning of quantization. Now, according to Bohr, he said the angular momentum of electrons can only have values that are multiples of h over 2 pi. Now, this is a very important constant. What is h? H is actually Planck's constant. Well, the idea of quantization was actually first introduced by Planck. Now, Planck's constant, let me see if I can give you the value of Planck's constant. Planck's constant is an important constant in nature, and it has the value h equal to 6.64 times 10 to the negative 4 meter squared kilogram per second. We will be using this very often. Now, once we are familiar with this h, we will be able to write expression for the energy difference between the two levels. For example, let me see if I can write that again. An electron moving from level 2 to level 1 will emit an energy that is given by E2 minus E1. And we can write this using H as E2 minus E1 equal to H times F. Now, this is an important relation. This is a quantum of energy. The difference between any two levels is Planck's constant multiplied by the frequency of radiation. That means you have a greater difference in the energy, you get a greater frequency of radiation. Now, you know about electromagnetic radiation. Red is low frequency, violet is very high frequency. So in order to get a violet color radiation, the difference in the energy must be much greater than when you obtain a red radiation. We will be looking at these as we move on. So according to Bohr, the energy of an electron is quantized. The angular momentum of an electron is quantized, and it can only have values that are multiples of h over 2 pi. For an electron in orbit, the centripetal force to keep the electron in orbit is actually provided by the electrostatic force between the electron and the proton. Now, let me say one thing here. The model of the atom that Bohr developed is using specifically hydrogen atom. Now, hydrogen atom has one proton in the nucleus and one electron. So, Bohr model of the atom is specifically for the hydrogen atom. Later on, we will see Bohr model actually breaks down when it comes to higher atoms. So, when you have one proton in the nucleus and one electron in an orbit around it, what is the electrostatic force between them? Each has a charge E, is that right? So that will be Q1, Q2 divided by R squared, where R is the radius of the orbit. So the centripetal force is actually provided by the electrostatic force between the proton and the electron. And we can write this relation. mv squared over r, which is the centripetal force, equal to k, the constant of Coulomb's law, q1, q2, q1 equal to q2 equal to e, and r is the radius of the orbit. Now, the angular momentum of the electron in orbit is m times v times r. Now, how many of you recall that from the first part of physics we did in the last semester? The angular momentum of an object of mass m moving with a velocity v at a distance r from the axis of rotation is m times v times r. We're going to use that over here. And according to Bohr, that angular momentum is quantized. The angular momentum has to be some multiple of h over 2 pi. and we have now used n as a multiple, where n can have the value 1, 2, 3, 4, and so on. That means if an electron is in the first orbit, n will have a value 1. The electron is in the second orbit, n will have a value 2, and so on. Now, we can actually solve for V from that equation. Can you solve for V from there? Now, V will be equal to, divide by Mr, it will be V equal to NH divided by 2mVr, isn't it? So, V equal to NH divided by 2 pi mR, and that is the orbital velocity of the electron. The velocity of the electron in an orbit, where n equal to 1 is orbit 1, n equal to 2 is orbit 2, and so on. Therefore, if you now come here, k e squared over r is mv squared over r, and I'm going to replace v by this quantity, nh divided by 2 pi mr. And what does that give you? Now, you must work it out along with me. Don't just watch it, but take a pencil and paper and work it out. Simplify this and see what that gives you. If you square this quantity, on the numerator there will be n squared h squared, and this will go to the denominator, will be 4 pi squared m squared r squared, and 1m, and that m will cancel. This r and the r squared will become r cubed. So the simplified form will be k e squared over r squared equal to n squared h squared over 4 pi squared m r cubed. Well, I hope you know what all these quantities are. E is the charge of an electron. Anybody recall what that value is? Charge of an electron? Well, let me see if I can write that down for you. Well, we have used these values earlier. The mass of the electron, this is the mass of the electron, and it is 9.1 times 10 to the negative 31 kilogram. The charge on the electron is 1.6 times 10 to the negative 19 coulombs. So you have k e squared over r squared. R is the radius of the orbital electron, equal to n squared h squared over 4 pi squared m r cubed. Well, we can do some simplification here. Let's see what we can do with this. Well, if r sub n is the radius of the nth energy level, well, what was the energy level? This is the first energy level, the first orbit. The second energy level, the second orbit. So r sub n, r1 is the radius of the first orbit, r2 is the radius of the second orbit, and so on. Then, if you solve for that Rn, can you do that from here? Solve for R. Well, you can see R squared on the left will cancel with R squared on the right, leaving an R there. And if you solve for that R, it will give you R equal to n squared h squared over 4 pi squared k e squared m. Or I write it like this, h squared over 4 pi squared k e squared m times n squared. Alright, this is a constant. H squared over 4 pi squared k e squared m is a constant. Alright, I want you to take your pencil and pen and work out the value of this now. I have given you the values of all these. H, you know the Planck's constant. K is the constant in Coulomb's law, which is 9 times 10 to the power of 9. E is the electron charge. M is the electron mass. Alright, take a piece of paper and pencil and see whether you can find the value of that now. Did you get a value for that? H is 6.64 times 10 to the negative 34 and square it. divided by 4 pi squared. K is 9 times 10 to the 9. E is 1.6, I messed it up there, times 10 to the negative 19 and square it, times m, the mass of the electron. And what does that give you? Well, did you get it as 5.29 or 5.3 times 10 to the negative 11 meter? And that will be 0.0529 n squared nanometer. And that is the radius of the nth orbit. If you put n equal to 1, you get the radius of the first orbit. N equal to 2 will give you the radius of the second orbit, and so on. Well, so Bohr is right on its way to find a much more viable model of the atom. Now, the energy En of an electron is E sub n. The energy of an electron in the nth energy level is negative k E squared over 2r sub n. Now, this is actually something that we've learned in mechanics. The potential energy of an object at a distance r is m1, m2 divided by r. Is that right? Negative g m1, m2 divided by r. And this is the same thing. Potential energy of an electron separated at distance Rn from the nucleus is negative k E squared over 2Rn. This is something we already did earlier. Now, if you now replace this Rn by the value of Rn that we calculated, or Rn equal to this quantity, and that becomes k E squared over 2, and Rn on the denominator became this quantity. And simplify that, you get the energy of an electron, a very important quantity. The energy of an electron is negative of 2 pi squared k squared e to the 4m over h squared times 1 over n squared. Alright, I want you to find the value of this now. Well, I calculated that as 13.62. So look at this quantity. Energy of an electron in the nth orbit is negative 13.62 over n squared. That's the n squared there. Electron volt. Well, the joule is a very big unit for measuring energy of an electron. So it is measured in a unit called electron volt. What's an electron volt? An electron volt is the energy needed to accelerate an electron when it is subjected to a potential difference of 1 volt. The energy acquired by an electron when it is accelerated by a potential difference of 1 volt is 1 electron volt. And what is the relation between a joule and an electron volt? Does anybody know? Well, 1 electron volt is 1.602 times 10 to the negative 19 joules. And it is a measure of the kinetic energy an electron will acquire when accelerated by a potential difference of 1 volt. Alright, let's do a small example. Find the orbital radius and the energy of an electron in the first excited state. Now, n equal to 2. N equal to 1 is called the ground state. N equal to 2 is the first excited state. N equal to 3 is the second excited state, and so on. So once again, when I refer to the ground state, why is it called the ground state? Because that's the lowest level. N equal to 1 is the lowest level, the ground state. So find the orbital radius and the energy of an electron in the first excited state of a hydrogen atom. What is the speed of the electron in this state? Well, we have obtained an expression for the energy already. Is that right? Well, we know that the radius r sub n is h squared over 4 pi squared k e squared m times n squared. When n equal to 2, you get the radius of the second orbit. So this is the radius of the second orbit. What we need to do is put in all those values and calculate that, and that will give you 0.0529 times 4 nanometer. This we calculated as 0.0529 nanometer. Alright, times 2 squared, which is 0.212 nanometer. And that's the radius of the second orbit. And the energy of an electron in that orbit will be negative 13.62 divided by n squared, n equal to 2. And that will be negative 3.41 electron volt. Alright. And what is the velocity of the electron in that orbit? V equal to nh over 2 pi mr. We had that again obtained earlier. So keep track of all these simple relations. And what all we need to do is now put in all these values where this r is this value. Well, this value. Alright? And that will give you 1.1 times 10 to the power 6 meter per second is the electron speed in the second orbit. But you need to do this all on your own. Don't just depend on me. Very often I make mistakes and you need to point out this to me. Alright. The allowed orbits are characterized by the energy of the electron in that orbit and are labeled n equal to 1, n equal to 2, n equal to 3, and so on. In fact, the first orbit is n equal to 1, n equal to 2, n equal to 3, and so on. And we talked about that already. Now, n equal to 1 corresponds to the lowest energy level, and we call that energy E1. And the lowest energy level is the ground state. If the electron receives a specific amount of extra energy, if you are able to supply some extra energy, now how can we supply extra energy to an electron? Well, we can actually supply extra energy to electron by heating an object. And you just saw I lighted up a hydrogen source. What I did, inside that source, you have an electrical discharge. When you pass an electrical discharge through a material, electrons receive extra energy. So, an electron in the ground state, if it is given some extra energy, now not any amount of extra energy exactly equal to the difference between these two levels, then the electron will absorb that energy and jump from n equal to 1 to n equal to 2. Or, if it gets exactly the amount of energy difference between n1 and n3, it will absorb that energy and jump from n equal to 1 to n equal to 3, and so on. So that's the mechanism. An electron can absorb energy and jump from a low energy level to a high energy level. Now, this electron is now said to be an excited. Once the electron has jumped from a lower level to a higher level, the atom is said to be excited. It is no longer normal. In a normal atom, you will find the electron in the ground state. Remember, we're talking about hydrogen atom. In a normal hydrogen atom, the electron will be in the ground state. The moment that electron has received extra energy and moved into an outer orbit, we say the atom is excited. Now, an atom or an electron cannot stay excited for a long time. It has to come back to normalcy. Now, how do an excited electron come back to its normal state? An excited electron has extra energy. If it has to come back to normalcy, it has to throw away the extra energy. Now, this is the mechanism of radiation. Now, this electron returns to one of the lower levels by throwing away the extra energy in the form of photons. In other words, light is made up of photons. Photons are these packets of energy. The packets of energy that is electrons, the excited electrons, throw away when these electrons jump from a higher excited state to lower levels. And that's very important. Now, look at this one here. An electron in the excited state n equal to 3, this is n equal to 3, has an energy E3. Here, electron has the energy E1. In the second state, it has an energy E2, E3, and so on. Now, if this electron, which has an energy E3, jumps to n equal to 2, so from the level n equal to 3, if an electron jumps to n equal to 2, that means an electron here has an energy E3. If it comes here, it can only have an energy E2. So if it jumps from n equal to 3 to n equal to 2, it has to radiate or throw away a certain amount of energy. And that is E3 minus E2. That difference in the energy is thrown away. And how much is that difference? Is h times the frequency of radiation. So E3 minus E2 is emitted as a photon of energy, HF, and that is the red radiation that we see. In the picture I showed you, there was a red light there, and the frequency of that red light is given by this, E3 minus E2 equal to HFR. In that case, what is the frequency of this color? Well, that is E4 minus E2. And the frequency of the blue color is E5 minus E2. And so on. So an electron jumping from n equal to 4 to n equal to 2 will radiate the extra energy E4 minus E2. And that will be h times the frequency of the green light. That is the green light. Doesn't look green, isn't it? Similarly, an electron jumping from n equal to 5 to n equal to 2 will give out energy E5 minus E2 equal to h times the frequency of the blue radiation. Now, look at the way Bohr's model is able to explain the observation. So, any model of the atom that we put forward, it must be able to explain all these observed phenomena. There you are. Now, radiations emitted by electron transitions from higher excited state to the first excited state. Now, previously we considered electrons jumping from the third excited state to the second, the fourth excited state to the second. In other words, all these electrons were jumping into the second excited state. Now, these radiations emitted due to these kind of energy radiations, that is, all the excited electrons jumping back to the first excited state, n equal to 2. Now, these radiations are called the Balmer series. In fact, the visible light that we have all around us is the Balmer series. And the visible light is emitted when electrons jump from higher excited state to n equal to 2. All right. And the Balmer series is this that we have, I started by showing you that series. All right. Now, what happens if electrons from the higher excited state jump to the ground state? The energy level there is, the energy difference there is very high. That means the frequency of those radiations will be very high. And those radiations are the ultraviolet radiations, because ultraviolet radiations carry very high frequency. So when electron transitions end on the ground state, they produce spectral lines in the Lyman series. Well, of course, it's the scientists who experimented with it. And these are the ultraviolet radiations. So ultraviolet radiations are obtained when electrons jump from higher excited states to the ground state. You got the Lyman and the Paschen series. Now, on the other hand, if the electron transitions end in the second excited state, from the higher excited state to the second excited state, that is called the Paschen series, and that is the infrared radiations. So look at the difference when electron transitions from higher excited state to the ground state. The energy radiations constitute what are called ultraviolet radiations. The higher transitions from higher excited state to the first excited state, n equal to 2, constitute the Balmer series or the visible light. And electron transitions from higher excited state to n equal to 3 constitute the Paschen series or the infrared radiations. Now, here I have the complete picture of all those. Lyman series, the ultraviolet radiations. Balmer series, the visible light. And Paschen series, the infrared. As we go from left to right, the frequency reduces. Now, a Balmer series for hydrogen, if you are lucky enough to see that complete series, it will look like this. You have a red, green, blue, purple, violets, and you will be able to see all those colors, which corresponds to all these transitions from higher states to the first excited state. Now, the energy difference between two levels is actually called a quantum of energy, and that quantum of energy is what we quantize as h times the frequency. And that quantum will come in different amounts depending on that frequency. So h times f, which is a quantum of energy, can have different values depending on the frequency or the color of radiation. The energy levels specified by N1, N2, N3, etc. are called the principal quantum numbers. So n equal to 1 is the principal quantum number 1, n equal to 2, n equal to 3, and so on. And so if you draw an energy level diagram, how will that look like? The lowest energy level is the ground state, n equal to 1. The higher excited state, the higher states are the excited state, n equal to 2, n equal to 3, n equal to 4, n equal to 5, and so on. So n equal to 1 is the ground state, and then you have the higher excited state. Now, the electron in a hydrogen atom will normally be in the ground state. If the atom is normal, its electron will be on the ground state. If the atom is excited, then the electron can be in any of these higher energy levels. Now remember, all our discussions are based on the hydrogen atom model. Now, higher temperature or electrical discharge, we talked about that. An external source of energy can actually give the electron extra energy, and these external sources can be higher temperature, heating, or an electrical discharge will result in an electron to jump to higher orbits or higher energy states. The energy of an electron in the ground state is negative 2.18 times 10 to the negative 18 joules. We actually calculated that earlier. So if the electron is on the ground state, that will be its energy value. And the energy of an electron in the first excited state is negative 5.44 times 10 to the negative 19 joules. And the third excited state, I have the energy all calculated. You can actually check this. You can put values in that equation and check these energy values. The energy of the electron in the ground state, the first excited state, the second excited state, and so on. Now you notice that as we go on, go higher and higher, these energy values are higher. Is that right? Can you figure it out? What is the difference between these two? What is this value minus this value? Is that a positive or a negative value? Try that on your own. Okay. Now, an electron will not stay in a higher excited state for long. We talked about that. An electron will jump from a higher excited state to a lower state by emitting a photon of energy. Now, if an electron jumps from n equal to 3 to n equal to 2, now tell me, if you remember, electron transitions from higher excited state to n equal to 2 is our visible light, isn't it? That's the Balmer series. So, what's the energy radiated when an electron jumps from n equal to 3 to n equal to 2? It will be this value minus this value. There you are. And I got this as 3.02 times 10 to the negative 19 joules. And I used red color for that because this is the energy of the red photon. Because when an electron jumps from n equal to 3 to n equal to 2, that particular transition results in the emission of the red photons. There you got the red. Now, this energy is the energy of the red photon. Now I want you to find the energy of each of the other transitions. Can you do that? What is the energy of the photon when a transition takes place from n equal to 4 to n equal to 2, n equal to 5 to n equal to 2, and so on? Do that on your own. There you are. There is a green photon, a blue photon, and a purple or a violet photon. Find the energy of